Okay, thank you very much. This is joint with Fedor Sandomirskiy, who's at Yale to Princeton. Okay, so what I'm going to be about is I guess it's a characterization of the Boltzmann distribution. And again, the math, you'll see some elementary question about polynomials. So I prepared for us some examples of polynomials over there if you want to see one. The whole thing is a bit wacky. It's not like part of some research agenda, you know. It's a question that is unrelated to other things that I do. And because it ends up being a question about polynomials, I have there's some non-trivial chance that this was all done by like people in algebraic geometry in the 60s or something. So please let me know if you've seen these sort of things before. I would not be surprised. Okay, so I want to start with a little bit of physics motivation. You don't really need to know any physics. You can ignore this part if you don't care. And then I'll give the formal math definitions and the result, and I'll tell you a bit about it. And I think there's some very interesting open questions. Okay, so what's the physics motivation for it? For the question is, we have the Boltzmann distribution 100 years ago. This was introduced, I think, by Boltzmann as something describing the distribution in which statistical mechanics systems can be found at a given temperature. And you know, he gave us sort of a proof or an explanation for why this is the distribution in which things are found. We're going to give a different one, but either way, you can actually go and take a box full of particles and shake it and see what the distribution of energies are, and it turns out to be the Boltzmann distribution. This is a very, very good theory. But I think that the current explanations for it, well, okay, this gives another explanation. So let me just give you a sort of a baby version of statistical mechanics. We're going to have a system. So this box is a statistical mechanical system. And we'll imagine that it can just be in a finite number of states. So maybe it's a spin that can only be either up or down. Okay. You have a particle in a box that can be in a continuum of states. It can have different positions and momentum. Let's just imagine that we have finitely many states that the system can be in. And in each state, there's going to be some energy. So maybe the energy here is 1, and the energy here is minus. Okay, we have a different system here where there are 3 possible states. And the energies are 0, 1, and 3. Now we're going to have some temperature well, the temperature is 1 over beta. Don't worry about what temperature. Well, I guess this is now going to be the definition of temperature if you don't know what temperature is, formally. And what Boltzmann says is, when the temperature is 1 over beta, there's going to be some probability that this particle, the system, is in this state or in this state. And what is the probability? It's just proportional to e to the minus beta times the energy. And here it's going to be e to the minus beta times minus 1. And of course, you have to normalize these to make it a probability measure. Okay. And here it's going to be e to the 0, e to the minus beta, e to the minus 3 beta. Okay. Now, one way to think about this is the following. Let me erase these probabilities. Really, I only care about the fact that the system has 2 states, one with energy minus 1, one with energy plus 1. And in fact, I don't even care that it has 2 states. All I care about is that half of the states have energy minus 1, and half of the states have energy plus 1. And here, 1/3 of the states have energy 0, 1/3 of 1. So maybe I have 6 states here. And both of these have energy 0, these have energy 1, these have energy 3. In order to state this Boltzmann theory, all I need to say is what fraction of each states have each energy. This I can describe by a probability distribution. It's like the empirical distribution of energies in the states available to the system. So here this distribution will be mu, which will be 1/2 delta at plus 1 plus 1/2 delta at minus 1, right? This is an empirical probability distribution over the reals. It tells you if I choose a state uniformly at random with probability 1/2, it's going to have energy minus one, probability 1/2 is gonna have energy plus one. And here, let's call this one eta, this will have 1/3 delta at 0 plus 1/3 delta at 1 plus 1/3 delta at 3. So far, so good. Now, one way to think of what Boltzmann tells you is, given a measure, say mu, of the empirical distribution of energies, the distribution of where the system is, where the particle is given by a new measure, which I'll call phi of mu. And the probability that phi of mu assigns to energy x is going to be mu of x times e to the minus beta x normalized. It's going to be proportional to this. Maybe let's write it out. This is going to be this divided by the sum over y, mu of y e to the minus beta y. So if we're going to denote by P of R, these will be the finitely supported probability measures on R. Then we have a function phi, Boltzmann's theory, phi at, I guess I should say, at a temperature beta, is a map that takes as an input, not NR, takes as an input this empirical distribution of states, how many I have or what fraction I have at each energy, and outputs the distribution of where I find the particle or the system, and it's given exactly by this. Okay, and when the temperature is 0, we just get mu back, so you get the uniform distribution over everything. Sorry, when the temperature is infinity,
yeah,
this just goes away. It's just 1. When the temperature is 0, we get a point mass on the highest. Right? The temperature is 0 corresponds to beta being infinity. So when beta is 0, which corresponds to infinite temperature, you just get the uniform distribution. When we take the temperature to 0, which means taking beta to infinity, this will converge in the end to just a point mass on the highest. So far, so good?
Is it crucial to be finitely supported?
It's going to be important for our techniques. So in the end, our theorem will be about finitely supported measures, which in the physics context corresponds to having finitely many states. But you can ask the same questions more general. Okay, so you know, why is this the way things work? You know, why do we have these things? So this function phi beta has two very nice properties. One property is very simple. I'm going to call it, you know, support preserving, or measure class preserving. It means that whatever distribution I throw in here, the output is mutually absolutely continuous with the input. What does that mean physically? It means that if I have a system with energy 0, 1, and 3, I'm going to find the particle at either energy 0, 1, and 3. There's 0 probability of having energy 17. And also all of these have positive probability. So support preserving, phi of mu of x is greater than 0 if and only if mu of x is greater than 0. The other important property is the following.
So these are statements for all beta, including 0 and infinity?
Not infinity, but 0 is. And it's going to be important because we're going to not consider the case of beta equals infinity. Okay. The second important property is the following. I'm going to put a big box around it. So imagine that this is one particle that can be into one of 2 states. This is another particle that can be in one of 6 states. I'm going to put a big box around these 2 particles. And I'm going to imagine they're just both in the same room, but they don't interact with each other. So the total energy of this, now this system has 12 states, 2 times 6 states. And the total energy is just the sum, right? So if we're here and here, the total energy is 4. Right, so I have a new system with 12 states, and the energy of each state is a pair of states, and the energy is the sum of the energy, which somehow captures that there's no interaction between these two particles. So what does Boltzmann tell us about this? Well, we could apply Boltzmann to this one and this one, and we get this. Or we can apply to the whole system. And what do we expect to see for the whole system? What do we want to see from a reasonable physical theory? Sorry? Yeah, go ahead.
Joint probability or some?
It's a joint probability distribution on these two systems. And what was a reasonable thing to demand of this joint probability distribution on this particle and this particle? Happen to be in the same room, but there's no interaction between them. It's independent, and more than that, just the marginal distribution should correspond. It just should be the product of the marginal of the distribution that we get for each one. Okay, and Boltzmann gives you this. Okay, what does this look like in terms of, so what is the empirical distribution of energies of these two systems together? If I have mu here and eta here, what is the empirical distribution of the combined system? It turns out it's just the convolution of mu and eta. Okay, so if you think about a random variable that's uniform has value of the energy that's uniform here, and another one that has uniform distribution over the energies here, the distribution of their sum is just going to be the distribution of energies when you choose something. Right? So this whole system has the energy is this convolution, and what Boltzmann gives you is, I'm going to call this being an endomorphism. I'll explain in a bit what that means. Endomorphism is that phi beta of mu convolution eta is phi beta of mu convolution phi beta of eta. So the distribution of energy is just the sum of these two independent distributions of energies. Okay, and I'm calling this an endomorphism because you can think of this set P of R as a semigroup. So I'm going to look at P of R as a semigroup with the operation of convolution. And this condition just means that this is a symmetry. This is a map from the semigroup to itself that commutes with the operation. It's a symmetry of convolution.
I want to go back to finite support means a finite number of points forms the support set. It doesn't mean compact support.
Yes.
And I don't see how it's being used in either of these conclusions.
It's not.
Not yet. It's coming later.
Coming later, yes. These two still hold for compact support. The only place where you start getting into trouble is if your tails are too thick that you can't normalize. But otherwise, this all holds. Okay. Good. So the question that we're asking is, are there other such things? Okay. So I'm going to say in general that phi, dot phi beta, is support preserving if it satisfies this. It's an endomorphism if it satisfies this. And I'm supposed to ask, what are all the support preserving endomorphisms of P of R? Okay. Now, you can also ask this by looking at other things other than R here. It turns out that for R, I don't know what the answer is. But I do know what the answer is for Q. So now I'm only allowed to have rational energy. But it turns out that this is an easy corollary for the same question for N, just integer energies, positive integer energies. Okay. So I'm going to focus on this case. I'll tell you a little bit maybe later about about the reals or about Q and Z, but it turns out that all the math meat is already in this case, where all these energies are natural numbers. Okay. Good. Another thing I want to point out is that this operation phi beta that we have here, this is also the tilting operation, like in large deviations. When you want to calculate large deviations, what you do is you apply this sort of transformation and at exactly the right beta, study what happens there. And then the reason this is so useful in large deviations is exactly because it commutes with convolutions. So that when I have the sum of IID random variables, it doesn't matter if I tilt each one of them or I do the tilting at the end, it behaves very nicely together. So another way of thinking about this question is what other sort of tilting-like operations are there? Yeah.
Can I ask you to review history? Is Boltzmann like 1870 and the tilting people are 1930?
Something like that. Kramer, 20s, maybe 30s, yeah. Gibbs was also maybe needs some credit here, I'm guessing. I think Boltzmann's maybe later. Maybe he died in the 1890s or something. I don't know. If somebody has a phone here.
But he did it a long time before people said large deviations.
Yes, definitely. Good. Let me translate this question to a different question. What I'm going to do is, instead of, I'm going to represent each one of these distributions by its probability generating function. Okay, so I have a distribution on the natural numbers. I'm just going to look at the polynomial. So if I have a distribution mu on the natural numbers, I assign to it a polynomial p, sum k equals 0 to some d, p sub k x to the k, where pk is simply the probability that mu assigns to k. Okay, so this is just a very simple mapping of every distribution of the natural numbers to a polynomial. And in fact, I'm going to identify the set of distributions. Let's change this also to n. I'm going to sort of overload notation and say that P of n is the set of all polynomials such that all these pk's are greater or equal to 0, and P of 1, which is the sum of these pk's, is equal to 1. Right, so this is just saying these are polynomials that are probability generating functions of some probability measure on the natural numbers. Does this make sense? Now, the nice thing to, the reason to do this is the following. What is, okay, and now again, I think of phi as a function from Pn to Tn, and support preserving, just like before, corresponds to phi of some polynomial p. This is a new polynomial. The kth coefficient is greater than 0 if and only if the kth coefficient of p is greater than 0. Convolution now just turns into multiplication. Phi of the product of two polynomials, p times q, is equal to phi of p times phi of q. Okay, because when you go from distributions to polynomials, convolution just turns into multiplication of the polynomials. Okay, so the question is completely isomorphic to asking the following question. I have these polynomials with non-negative coefficients that sum to 1. I have some map from this set to itself that preserves the positive coefficients, the locations of the positive coefficients, and commutes with multiplication. Does it have to be of this form? So what does this form mean? In terms of polynomials, it means that phi beta of a polynomial p is the polynomial p evaluated at e to the minus beta times x, and then normalized by p of e to the minus beta. So it's just a change of variables. When you think about it in terms of polynomials, all this does is replace the variable x by e to the minus beta x. You can plug that in and, reverse, it's just a matter of notation. Okay, so what other functions other than just this change of variable and renormalization have this, right? So, I mean, when you do a change of variable like this, somehow you're changing the units of the variable x, obviously this has these two properties, right? The question is, what else is there? Okay, now what I want to do is, when I talk about polynomials, these normalizing constants are kind of annoying. I don't want to have to carry them around. So I'm going to get rid of them. Okay, so let me leave this here in blue. But if I just told you this without the blue one, you can always normalize later. So I'm going to write down a lot of polynomials that are going to have non-negative coefficients. I'm not going to normalize them to 1, but I just don't want to keep on writing these constants everywhere. You can always just add them later if you want. Okay, do tell me if it's confusing at any point. Okay. Good. So let's try to understand what other phi's like this there should be. Okay, so let's imagine that we take some phi such that phi of the polynomial 1/2 x plus 1. Okay. Just as again, this polynomial corresponds to the distribution that puts probability half on 0 and probability half on 1, right? These are the exponents here. Imagine that phi of this is, I don't know, 1/3 2x plus 1. Say I tell you that phi has this property, so suppose phi has this property. And I want to know, what other constraints does this put on phi? That makes sense? I want to know, given these properties, what does it tell me about the rest of phi? Can I choose just whatever I want for other polynomials? Let me drop the normalization again. Okay, so I'm gonna, right? So when I write this, I mean what was written here before, but I just don't want to worry about normalization. Yeah.
So at this stage, you're thinking of phi as a generic guy that satisfies these two hypotheses,
Yes.
and not one of your phi betas.
Exactly. So suppose phi is a support preserving endomorphism, and this holds. Well, what do we know? We know, for example, that phi of x plus 1 to the n has to be 2x plus 1 to the n, right? What do we know about phi of 3x to the 17 plus x to the 144? Does this choice in any way constrain this choice? Right? How would I somehow use these constraints to go from here to here? It doesn't seem like there's a way. So I could just, specify anything here. Maybe this goes to, I don't know, x to the 17 plus 3x to the 144. It has to be 17 and 144, right? Because of the support preserving property. But this does not seem to be inconsistent with this. Okay? So
in your original family parameterized by beta,
yeah,
you could solve for beta based on this first fact.
right. So if I told you it was in that family, and I told you that it satisfied this, you can now calculate beta and it constrains everything. It tells you everything, right? So in fact, if I throw in anything that's not a point mass, so just x to some power, you can back beta out of that, right? So if you know its value, just one system that has more than one state, has anything non-trivial, it tells you what beta is. But seemingly, if all I know is that it has these properties, then this doesn't seem to constrain. So let me go a bit further with this line of reasoning. I'm going to say that let's put if p of x is equal to some r of x times q of x, and this is for p, q, and r, all in the set of polynomials that I'm interested in, then I'm going to say that p is reducible. Otherwise, it's irreducible. So what does this correspond to? Again, in terms of measures, it means that this probability measure is the convolution of these two probability measures. And I want these to also be in my set of things that correspond to probability measures. I should also say maybe R and Q are different than just the identity, the polynomial is just one. Okay. So now I can take any polynomial P, whether it's irreducible or not, I can always write it as a product of irreducibles. So if we want to construct a phi that satisfies this, what I can do is just choose for every irreducible something that satisfies the measure supporting constraint. That now defines it for all the reducible ones. And I have this huge family of things that I can build, okay? Unfortunately, this is wrong. So where am I cheating? So I think it looks from the faces like I managed to deceive you. Yes.
Unique factorization.
Yes. So
Because you're cheating by using the word you're cheating by using the word reducible and irreducible, which already had a meaning in algebra.
so this is not a unique factorization domain. Okay, so there exists P1, Q1, P2, Q2 irreducible such that Q1, Q1 is equal to P2, Q2, and I guess they should all be different from each other. Okay, distinct. Okay, so what does that mean? It means that if I take, it means that phi Q1 is phi of Q1 is equal to phi of P2 times phi Q2. So if I choose, and these are all irreducible, if I choose what this, and this is, it fixes this for me. So I don't have freedom to choose it for every irreducible. So the question is, how many constraints do I get from this lack of unique factorization? That's what the question boils down to. Okay, so now let me tell you the theorem. I'm going to phrase it in terms of polynomial. I guess it doesn't matter. For every support preserving endomorphism phi, there exists a beta such that phi equals phi. And that's everything. And in fact, if I fix phi at just one thing, it fixes, there's so many constraints that it fixes it for all of them. Okay, so somehow using these two things, I can go from this to this. And in fact, exclude this. This is impossible because this tells you already that beta is positive. So here the temperature can also be negative. Here, the temperature is positive, but here it's negative because I've put more weight. Sorry, no. Here, no, okay, if I said this, this would be impossible, okay? But okay, it doesn't matter. Once I see this, I know exactly what the answer to this is gonna be because I can back up it. Okay? So, any thoughts or questions about this?
Is it obvious that the decomposition is not unique? I'm thinking of it.
No, you need to go to like degree 6 or something to come up with examples.
Okay.
But this, I mean, if people in probability sort of know this fact that you can convolve different things and get the same answer. We have or at least we used to have an example in the paper, but you need to go up to.
That I feel better.
Wasn't crazy dice
I don't know.
called an example?
I don't know this example. Oh, crazy dice. I'll look it up.
I forget the name, Schlescherman's. If you look up crazy dice on the wiki, they'll tell you the name of the
All right,
original.
all right. Okay, so how do we prove this? What we want to do is we have a problem with this unique the fact that this is not a unique factorization domain. Now, when I have a polynomial, I can actually, the set of all polynomials is a unique factorization domain, right? If I have a let me give you an example. I have a polynomial p of x equals x squared plus 1. According to my definition, this is irreducible. Turns out, okay, so but I can write it as x squared minus x plus 1 times x plus 1. Right? Problem is that this thing is not, it has a negative thing here. So I don't know what phi assigns to this thing.
I mean x cubed. X cubed.
Yes, sorry. Okay. But polynomials, the set of all polynomials is a unique factorization. This is the fundamental theorem of algebra, right? Right, each polynomial, if I'm over the complex numbers, I can write it as a product of linear terms. If I'm over the reals, I can write it as a product of linear and quadratic terms, right? I put together each complex root with its conjugate, and I get these quadratic terms, but I can, so what I want to do is, I want to enlarge the domain of phi to something that is a unique factorization. And this is going to be the following. I'm going to define m of n. Okay. Let me write it over there, actually. I'm going to define m of n as the set of all polynomials such that p of x is greater than 0 for all x greater than 0, and p of 1 is equal to 1. So what am I doing here? Instead of saying that the coefficients are positive, I'm looking at polynomials that are positive for positive x. Obviously, this is a bigger set than this, right? Whenever my polynomials have positive coefficients, it's good. They're going to give me a positive number for positive x. But this is a larger set. What's an example of something that's in the difference between these? This. Okay. In fact, here's another way of thinking about this. Instead of this, I could have written, or I guess instead of this, I could have written p of x is just different than 0 for x greater than 0. These are polynomials without positive roots. Okay, right? Because if I do have a positive root, then it's going to be negative. The polynomial, it's going to be negative for something before or after the root, right? So this m of n is the set of polynomials that are normalized, so that p of 1 is equal to 1, and have no positive roots. This is a unique factorization domain, right? I can write, so if q of x is in mn of x, then q of x, it's going to be something like x minus a1 times x minus a2, x plus, I want this to be, these are going to be, it's going to have some negative roots, right? And so on, x plus some an. And then I'm going to have terms like x squared plus b x plus c. And then I'm going to have terms like x squared minus dx plus e. But this d can't be big enough so that I actually have positive roots. These are going to have no roots at all. Right? So these are going to have negative determinants. But this is now the unique factorization. So what I'm going to do is I'm going to prove the following claim phi can be extended, or phi, I should tell you, phi that's defined on just the probability measures can be extended to a phi defined on these things such that it's still multiplicative. Phi of PQ is phi of P times phi of Q. And it turns out that there's also a unique such extension. By the way, this is defined as a set of polynomials, but you can go back now to measures and ask yourself, okay, what kind of measures are these? These are now signed measures, because some of these coefficients can now be negative. But this means that they have a positive moment generating function. So this corresponds to measures supported on the natural numbers, signed measures, still probability measures that have a positive moment generating function. In terms of the physics, because these things are negative, you have a system with some number of states at energy 1 and negative 7 states at energy 2. What does that mean? I don't know what it means, but it still has a positive partition function. So you have a partition function that you can work with and reason about and try to do stuff with. Okay. And in fact, what this tells you is that if you have a theory that is a reasonable theory, it's one of these support preserving endomorphisms that is one of the things that does what a physical theory should do. It also gives you, you can extend it to these sort of systems. And I talked to some physicists and, there might be some things where, we're trying to think if there's actually some system that you can model by having these anti-states that don't exist.
So in this claim, you had support preserving and endomorphism. And in the conclusion, you're giving up support preserving?
It turns out that it will be support preserving, but that is almost the same as proving the whole theorem. It will be support preserving in the end because it's just going to be this Boltzmann thing. But that's more or less the same as proving. Okay, so.
But then there's no entropy, right?
Sorry?
There's no entropy.
What do you mean? Once you have these negative things. Right, because how do you take the log of these negative things? But you do have this moment generated. Okay. So, how do you extend this? So here is a lemma. This is the key for extending this. It's a very simple lemma. It says the following: for all Q in the set M, there exists a P. That's a real probability measure. So I have one of these signed probability measures. For each one of these, I can find some P that's a real probability measure, such that Q times P is again a probability measure. For each one of these polynomials that has some coefficients or maybe negative, I can multiply it by something here so that suddenly all the negativity disappears and you end up with a positive polynomial, a happy polynomial. And so how do you prove this? Well, it's enough to prove it for linear and quadratic things, because if I can find a P that works for this and another one that works for this and for this and for this, I can take their product, multiply this whole thing by their product, it'll work for each one, right? So it's enough to prove this. Now for these terms, I don't need, these already have positive coefficients. For these, I don't need positive coefficients. So I just need to look at things like this and find something to multiply. It turns out that there's still some work to do here, because depending on the relation between D and E, what you multiply by could be of arbitrarily high degree. Okay, so you might need to take pretty high degree. It's not hard to prove. Now, when we proved it, we're sort of like, wow, this is kind of crazy. We're surprised that it was true. And like, oh, this is kind of crazy. But then we're like, okay, there's no way that this is not known. It's such an elementary thing. And it turns out that we were just scooped. This was proved by Poincaré in 1883. Okay. 83, let's see. Yes.
What was the case?
Oh, and I made an awful mistake. There we go. Yes.
What was his motivation?
So there's this thing called Descartes' law of signs, which says something about the number of times the coefficients go from positive to, I don't remember, and he was proving a converse to it. So that's what, that's how I understand this. Okay. There's a theorem by Polya from maybe 28.
For sure the L goes before the Y.
Thank you. That says so this is Polya's positive Stellensatz. And it gives the same statement, but for multivariate polynomials. Okay. One thing that follows from Polya's theorem, but it's actually very easy also, these things are all very elementary, is that you can take, for all c greater than 0, there exists all n, for all n large enough, you can take p of x to be x plus c to the n. So this p that I want here, depending on q, I can take any c. If I take large enough n, this p will work. And I'll actually be using this. Okay. Now, what is this? You know, if you take x plus 1 to the n, x plus 1 is just Bernoulli half. This in general Bernoulli. This is what's it called, a binomial random variable. So it's something, you know, if you take something that's close enough to a Gaussian, it works. This is, if you want to think about it just in terms of probability. Take something close enough to a Gaussian, convolve it with something of this form, you get a probability. And I think a Gaussian actually works, but it's not necessarily going to give you, it's not going to give you something supported on the natural. Okay, I'm not sure that Gaussian works. Let's go back. This one. Okay. Okay, so how does this help us? Well, it's actually easy from here. Let me write it over here. So given support preserving endomorphism phi, we can extend it by just defining what should I define phi of q to be? I wanted to satisfy this. Let me write this a different way. I want phi of q to be phi of pq divided by phi of p. So let's just put that in the definition. I'm going to define this to be phi of q times p divided by phi of p. But where I choose p now using this lemma. Okay, now I know what this is because it's actually a real distribution. This is also a real distribution. So this is going to be my definition for phi of q.
Doesn't depend on n, or so there could be lots of, like you say, for
There could be a lot of different p's. It turns out that it doesn't matter. So that's a very simple thing. You know, if phi u p1 divided by that's so let's just say that what I want to look at, imagine that this holds also for both for p and for r. So also q times r and p of n. That means that q times p times r. Because this is already all non-negative. So if I multiply it again, it stays non-negative. So okay, now I'm improvising this, but it's something like phi of q
So it will be
PR. Sorry, you see it? Tell me what to write.
over 5p by r.
Yes, over 5.
Phi of what? Phi of q is like this is phi of q
PR
PR
over 5p by r.
over phi of PR. Now we're,
Both are equal to the.
this is, I can take the R out of both of these, but I can also take the P out of both of these, and it's the same thing. Okay. So this is well defined, it doesn't depend on the choice.
But it has outputs in rational functions.
Yes, good, you stole my next bullet point.
Sorry.
Now it's a rational function, but I promised that the extension is actually here. So let me show you how to prove that this actually is always in here. How much time do I have?
4 minutes.
I have 4 minutes.
Extendable to 11.
10 minutes.
Oh, yeah, because you could eat into your own question time.
I've already eaten into 11 minutes
Yeah,
worth of
10 minutes.
questions.
Let me at least show you. Let me try to show you this. Okay, so for this, I prepared some stuff here. Let's erase all this. So I'm going to define a family of polynomials. This is Q indexed by A and B, where 0 is less than A, less than B. Okay. And it's given by this A squared minus AX plus AB. And you can check that these are in here because A is less than B. That's why I chose AB here. Okay. Now I pre-calculated this. If you multiply it by X plus A, you get this. If you multiply by X plus B, you get this. The important thing is that this does not have a quadratic term. And, oh, sorry, this should be squared here. And this does not have a linear term. Okay. How does this help us? Now we can finally use this support preserving condition. So what do I know? I know that phi of this QAB is, oh, sorry, and also importantly, these are both non-negative polynomials with non-negative coefficients. Okay, so right down here, phi QAB, it's phi of this divided by this, right? So this is phi of x cubed plus AB minus AX plus A squared B divided by phi of X plus A. And this is also equal to phi of X cubed plus B minus A X squared plus A B squared divided by phi of X plus B. So far, so good? Because it's well defined. Now, this is different than this. Phi of this polynomial has to be different than phi of this polynomial by the support preserving property. This has positive coefficients only here, here, here. This one has positive coefficients here, here, and here. So these two are different from each other, which means that these two are different from each other. So we get that if A is different than B, then phi of X plus A is different than phi of X plus B. So on these linear polynomials, and remember now we only, because we've extended it, we only care now about linear and quadratic polynomials. On linear polynomials, we suddenly get that this phi is a bijection, which is already kind of an interesting non-trivial thing, right? From the support preserving property. So we get that phi is a bijection. How does this help us? So what I'm going to do now is I'm going to use Polya's. I'm going to use Polya's theorem. And I'm going to say the following. I'm going to say that phi of Q is equal to phi of q of x times x plus 1 to some n large enough, divided by phi of x plus 1 to the n, which is going to be some x plus some a to the n. Right, so phi of x plus 1, we know that that's some x plus a. And phi, oh, not a, sorry, we already used a, c. And phi of x plus 2 is going to be x plus some d, with c different than d. Because, right, that's what we just proved, that these two numbers are different from each other. So this is going to be x plus c to the n. It's also going to equal phi q to the x plus 2 to the n, divided by x plus d to the n. And now here's what we're going to do. These polynomials, which come up as probability generating functions of these measures, we're going to look at their roots. And it's a little mysterious to me why the roots, what is the meaning in terms of probability of the roots of a probability generating function? Okay, but the roots of these polynomials are what you have to analyze to understand everything that's going on. Okay, so we know that this is equal to this. What I'm going to do is I'm going to cross multiply. I'm going to move this to here and this to here. So pardon me, I know I'm out of time, but I need to write this down. Q of x plus 1 to the n times x plus d to the n is equal Q of x times x plus 2 to the n x plus c to the n. So I have two polynomials, right? This is a polynomial because this thing is positive, right? This has positive coefficients also here. So I have here an equality of two polynomials. So the roots have to be the same. Now this one has at least n roots equal to minus d. This is the polynomial on this side. Which means that, right, this one here. This polynomial, because of this, has n roots that are equal to minus, at least n roots that are equal to minus d. Which means that so does this one. But none of these are roots that are equal to minus d, because c is different than d. Which means that this polynomial has to have n roots equal to minus d. This polynomial is this. So this has n roots equal to minus d. So when I divide it by x plus d to the n, I'm left with a polynomial. Sorry, this is in M. Okay, so that's where you don't get a rational function, but you actually get a polynomial. So I'm unfortunately out of time. It turns out that the proof is you have to do a lot of exercises like this one. You have to come up with different polynomials, decompose them. And each time you do this, you get more constraints and you can start reasoning about what happens. And I think it'd be a bit boring to show all these steps, and I'm out of time, but this is the kind of analysis they have to do, and then reason about the roots of these things. Let me say two more. One is two more things. For people interested in algebra, you can consider only, instead of Pn, consider only polynomials of this form that have rational coefficients. And do this, start the whole thing again. So I want now probability measures. All the probabilities are rational numbers. The set of polynomials with rational coefficients, it's important in algebra. And the thing is, you can still do this extension, define it the same way. Again, just this with the additional thing that all these coefficients are rational. But now the decomposition into irreducibles is not so simple. You have a lot of crazy irreducible things. The theorem still holds because it turns out that there's some surprising continuity that you get here. And again, I'm just going to leave it as a very mysterious statement, but the same theorem is true even if you just are interested in rational polynomials over the rationals. One last thing I want to say is, instead of probability measures over the natural numbers or the reals, you can think about probability measures over r squared or z squared or n squared. This corresponds to probability distributions, multivariate probability distribution. Now you can still do tilting, and it's very useful to do tilting in higher dimensions, but are there other things? And these techniques break down. So we don't know how to answer the same question for probability measures on z squared or for polynomials of two variables. Are there other support preserving endomorphisms? We don't. Okay, now I'm really out of time, so thank you.
Yeah, I think we have time for like one or two questions, so whoever wants to. Go ahead.